Continue our series on the 2016 CCEA GCSE Physics paper, Unit 2, and we're doing question 3, which is electricity. 3A. A student was given a resistance meter which measures resistance directly and a length of nichrome wire. She connected the circuit shown below and recorded the resistance of various lengths of wire. Here as a table of results then, so it says that her results are recorded in the table below. So we've got length of wire in meters and we've got resistances in ohms. So 0, 0, 0.25 of a meter. So it's gone up in 25 centimeter jumps and we're getting an increase in resistance. Using the results in the table and the grid below, plot a graph of the points and draw a line of best fit. So I brought back the table of results and you can see we need to get at least to 17. The length axis has already been marked out for us, so we need to figure out a scale for this. And probably the most obvious resistance scale would be 5, 10, 15, 20, and that will cover us all the way up to 17. And so the rules about picking a scale for a graph is that you need to get at least past the halfway mark, and we're going to be plotting 17 round about here, so that'll be fulfilling that criteria. So 0, 0 is a point, 0.25 and 4 is a point, 0.5 and 7, 0.75 and 12, and finally 1 meter and 17 ohms. So we're also supposed to put a line of best fit through these, and that's going to be about there. Part 2. The relationship between the resistance R and the length L of the wire is of the form R equals K times L. Explain how you could obtain a value of K from the graph. Okay, so this is in the form of Y equals mx. If you recognize the equation of a straight line, if we're plotting R up the side and L along the bottom, then K is going to be the gradient of this line. Using your graph, find the value of K and include a unit for it. So we want to get a rise over run here, and there's a nice easy section going across here and up here with a very defined rise and run because this value here is right on the graph. So we can just use the numbers for that value, and those numbers were 0.75 and 12. So we can just use those numbers to find the gradient. So it's 12 over 0.75, and that comes to 16. Part B. Nichrome wire is often used to make the heating elements for electric heaters. And here we have an old style electric bar heater. The heater has an electric power rating of 720 watts when operated from 240 volt main supply. Calculate the resistance of nichrome wire used in the heating element. So this is relating power to voltage and resistance, and so we need an equation for that. And so power is V squared over R, and so R will be V squared over P. So that's like 240 squared over 720, and that gives us an R value of 80 ohms. Part 2. The nichrome wire used is known to have a resistance of 40 ohms per meter of length. What length of wire is required to make the heating element? So we need 80 ohms and we've got 40 ohms per meter. So to get 80 ohms we're going to need 2 meters worth. That'll give us 2 40s, which will be 80 meters. So 2 times 40 is 2 40 ohm single units of it, and each one of those is a meter, so 2 times 1 meter gives us a value of 2 meters. The production company have decided to use wire of double the cross-sectional area of the previous wire. So we have the original wire here, and then we have the new wire, which is twice the cross-section. What effect will using this new wire have on the resistance of the heating element if the length of the new wire used is the same as that of the original wire? Okay, so we've got the same wire but we've doubled the cross section. Well, that's going to halve the resistance. So we say that resistance will be halved. To have a heating element of the same resistance as before, what length of the new wire compared to the original is needed? Well, the bit that we have is half of what it needed to be, so if we double that length we'll get it back to where it should be. So length needs to be doubled. Part C, the circuit below was set up. The ammeter reads 0.2 amp and the voltmeter 4.8 volt, which meant the wire had a resistance of 24 ohms. The wire was removed and shaped into a circle with the voltmeter connected across the diameter of the circle as shown below. So the wire, when it was stretched out, was 24 ohms. Now the same bit of wire has been made into a loop. So these are like two sections in parallel with 12 ohms worth of wire here and 12 ohms worth of wire here. So this is like a section with two 12 ohm resistors sitting in parallel. And this is the important part about this question. You need to recognize what's happening here. That this is a 12 and a 12 in parallel. Part 1, what would the voltmeter read now, or now read, sorry. So we need to look at that circuit again. So I've brought this wee circuit back in, and remember we have the 12 up here and the 12 down here. 24 ohms worth of wire split like this gives us a 12 and a 12 in parallel, and the smart amongst you will realise that that then will behave like a 6 ohm. Sorry, that's not very neat, but there you go. It'll behave like a 6. The voltmeter before read 4.8, and that'll be the same because it would have been reading the voltage of the power pack here, and it will continue to read that. So that's really what you want to explain here. So your battery voltage is going to be the same because it's the same set of cells as the original question. What would the ammeter now read? Well, this is now where we look at the idea of having 4.8 volts across a 6 ohm resistance. So we just do an Ohm's law calculation for that. So we just point out that The 12s in this arrangement is the same as a single 6, and then we just do I equals V over R for that, which in this case is going to be 4.8 over 6, and that would be 0.8 of an amp. Part 4, explain how you arrived at your ammeter reading, and what you're going to need to do here is explain what was happening with the resistance when you put it into a loop like that, and that becomes 6 ohms, and then you're doing Ohm's law for the total resistance of 6 ohms. So you just fill in that explanation with the value of the resistance and then the Ohm's law calculation. Okay.